All right, this is part two of concept 32. So it deals with elimination again, but we're just going to have a few additional steps we need to take in order to get the equations to look like the right form in order for us to eliminate the variables. So if I have a system where the variables are not canceling out, I need to transform them in order to make them cancel out. And the way I do that is by multiplying the equation or equations by a constant. Okay, so a whole number. And it could be positive or negative. I guess it doesn't necessarily have to be a whole number, but that's the best case scenario. It's the easiest way to do it is multiply by a whole number. So after we multiply one equation or both equations by a constant, then we solve it just like we did in part one. But we're sort of manipulating the equations to get into the right form. So let's take a look at this first example here. If I have a situation like this and I tried to eliminate the variables by adding them together, I would get something like this. 4x minus 5y is equal to 5. And that doesn't really help us because I don't know what x is, I don't know what y is, so I can't really solve this equation. But what I can do is make the equation look like what it needs to in order for it to cancel out. So for example, if I wanted to cancel out the x's, I know that they need to be the equal, like the same number, but one's positive, one's negative. They need to be additive inverses or opposites. So if I have positive 6 and I want to make negative 2 into negative 6, I would need to multiply negative 2 by 3. The problem is that I can't just multiply one term in the equation by 3. I have to multiply the entire equation by 3. So it sort of looks like the distributive property in a way, where I multiply the whole equation, the second equation, by 3. So what I'm going to do is I'm going to rewrite my first equation. My equation is unchanged. I didn't do anything to it. But my second equation looks like this. When I multiply 3 times negative 2, I get negative 6x. And 3 times 5y is 15y. And 3 times 15 is 45. Now it looks like I can cancel out my x's. So from here, we're going to do exactly what we did in part 1 and combine the terms and then solve for the variable that we are looking for. So since the x's cancel out, I leave them alone. They go away. And I have negative 10y and 15y. That gives me 5y. And negative 10 and 45 becomes positive 35. From here, I'm going to divide by 5, like before. And my y is equal to 7. From here, you could take your y and plug it back into one of your equations to find your x. So just as a recap from part 1, I would take my first equation, for example. You can pick either one, but I'll pick my first equation. So 6x minus 10 times 7 is equal to negative 10. I'm taking my first equation. So I get 6x minus 70 is equal to negative 10. I'm then going to add 70 to both sides. And I get 6x is equal to 60. I then divide by 6 on both sides, and x is equal to 10. So our first answer for our point where these two lines intersect is 10, 7. So even though initially it didn't look like the variables could cancel out by manipulating the equation or transforming the equation, I can make them cancel out. Here we have a special case where I want to be able to cancel out one of the variables. So similar to what we did up top, I need to make sure that they're the same number but opposite signs. They're additive inverses. So if I wanted to eliminate the x's, for example, I know that -2 needs to become +8. And how I do that is I multiply it by -4. If I multiply this by -4, I get +8, and that way they will cancel. So we're going to multiply the second equation by -4. So again, I'm going to rewrite my first equation because it hasn't changed. And now I'm going to write my new second equation after I've transformed it. So -4 times -2 again is +8x, and -4 times 3y is -12y, kind of interesting. And 6 times -4 is equal to -24. So when we go to combine these, what we see is that the x's do cancel out, but the y's are going to cancel out too. The y's are going to cancel out too, so it's kind of interesting. And then we have something over here. So let's see what that looks like. This is 0. This is 0. The x's cancel out to become 0, and the y's cancel out to become 0. And over here I have 3 and -24, which gives me -21. This is kind of an interesting case because 0 is not equal to -21. Since this is a false statement, since this right here is a false statement, that means there is no solution. If you remember from part 1, if we get a true statement, in this case, it would be infinite. But if we get a false statement, it would be no solution. So that means that on a graph, these two lines do not intersect. They're parallel. So they're never going to cross. That's why they have no solution. Let's take a look at a couple more examples. Now here we have yet another interesting case. Again, if I were to combine any of these, combine these two equations by adding, they wouldn't cancel out, but I need them to. And there's no whole number that I can multiply by 4, for example, to get 5, or 5 to get 4. But it's also possible that I can change both equations. I can transform both. And that's exactly what I'm going to do. If I were to take my first equation and my second equation and multiply them by different constants, I can get them to cancel out. So if I wanted to eliminate the x's, for example, I would multiply this by 5 and this by 4, because 5 times 4 is 20 and 4 times 5 is 20. And that solves half of our problem, because at least we've got the number to be the same. What I also need to do is make sure that they have opposite signs, however. So I can pick either one and make one of them negative. So I will make my second one negative. And again, it doesn't matter which one you make negative, you're going to get the same result. So let's go ahead and rewrite these equations after I've transformed them. So my first equation, my top equation, becomes 20x minus 25y is equal to 25. And my bottom equation becomes negative 20x plus 24y is equal to negative 28. Now I have a situation where I can cancel out the variables. well, one of the variables anyways. So the x's go away, and I get negative 25y plus 24y is equal to negative y, and 25 and negative 28 combine to become negative 3. And finally, I would divide by negative 1 on both sides. So y is equal to positive 3. Of course, we would then go and plug it back into our equation to get our x. And you can pick any of the two equations that we started with, or you could even pick any of these two that we ended up with after we transformed, and you'll get the same result. But we'll go back into our second equation, for example. So 5x, or 5 times x, minus 6 times 3 is equal to 7. So I get 5x minus 18 is equal to 7. I'm going to add 18 to both sides. So 5x equals 25. And then I would divide by 5. And x would be equal to positive 5. So our final result is 5, 3. That's the point where these two lines intersect. Now, I want to highlight that you could, again, change either, if you wanted to get the x's to cancel, you could do that, but you can also cancel the y's. So like, for example, if I wanted to cancel the x's, I needed to find the least common multiple between 12 and 8, in this case to be 24. So if I took my first equation and multiplied it by 3, and my second equation and multiplied it by 2, I would get positive 24 and negative 24, which is perfect, and that's what I would want. But I also want to highlight that if I wanted to cancel the y's, for example, I have 4 and negative 6. Well, 12 could be the least common multiple, so I would multiply the top equation by 3, and the bottom equation by 2 to again get our result. So it's just finding what you're looking for to multiply in order to get the variables to cancel out. And that's elimination for systems of equations, part 2.